So here again, in this case, we're given a known power series and we're asked to find the power series of a new function. And the technique that we're going to use then is differentiation of power series. So let's see how that works. So the idea is that we're given a power series expansion that has an interval of convergence from a minus r to a plus r. And so this power series happens to represent the function known as f of x. Well, if we take the derivative, so if that function f is going to be differentiable on that interval for which the power series is convergent, then we can take the derivative of the power series term by term, and that will give us a power series representation for the derivative of our function f of x. And furthermore, the interval of convergence, or our radius of convergence, for our new power series, for our new function, is the same as the radius of our original function. And kind of by that same token, if we integrate our power series term by term, then that will give us a power series expansion for a new function, which is the integral of our original function f of x. And once again, just in the case of the derivative, our radius of convergence stays exactly as it was for the original function. So with that in mind, let's take a look at cosine to get an expansion for sine. So we know that for our expansion of cosine, we're given a series n equal to 0 up to infinity of minus 1 to the n over 2n factorial nx to the 2n power. And this one is actually valid on the entire real number line from minus infinity over to infinity. Well, if we take the derivative of both sides, what happens, so the derivative of cosine, and then our power series, we can take the derivative term by term. So we have the derivative of minus 1 to the n, x to the 2n, over 2n factorial. Well, on the left-hand side, we just get our minus sign. And then on the right-hand side, our minus 1 to the n over 2n factorial is just a constant, so that can get pulled to the outside. So we have the sum from n equals 0 to infinity of minus 1 to the n over 2n factorial, and then the derivative of our x to the 2n, which is 2n times x to the 2n minus 1. And so now we can go through and kind of simplify this a little bit to get our expansion for sine. So one thing that we notice in this case, when we do our expansion, if n is equal to 0, well, we have a 0 term. And so this is really the same thing as if we start our power series expansion not at 0, but if we started it at 1, going from 0 up to infinity. And so then we have minus 1 to the n over 2n factorial, and then we have a 2n x to the 2n minus 1. Well, if we write out what that 2n factorial looks like, so we have a sum n equal 1 up to infinity for, we've got a minus 1 to the n, and in the denominator, we'll have 2n minus 1, 2n minus 2, all the way down to 2 times 1. Then in the numerator, we've got our 2n and our x to the 2n minus 1. So that what happens in this case, our two n's cancel out, and we are left with n equal 1 up to infinity for minus 1 to the n over, so we've got our 2n minus 1, 2n minus 2, all the way down to 1. Well, that is actually our 2n minus 1 factorial, and then we have an x to the 2n minus 1. Well, now traditionally what we tend to do in this case, well, we can move that negative. So this is really up here at the front. We had a minus sign. Well, if we move that negative over, then what happens is we have that the sine of x is then equal to the negative sum n equal 1 up to infinity of minus 1 to the n over 2n minus 1 factorial x to the 2n minus 1. So I can move that n to the inside, or I can move that negative to the inside, and so I have minus 1 to the n plus 1 over a 2n minus 1 factorial x to the 2n minus 1. Well, now traditionally what we do is to start our power series at 0. And so if I do a change of index, so if I make m equal to n minus 1, then what happens, my m plus 1 is equal to n. And so my series, when n is 1, 1 minus 1, m starts at 0. As n goes to infinity, m goes to infinity. So I have a minus 1. N being m plus 1, so I have m plus 1 plus 1. In the denominator, now my 2n minus 1, if I do that substitution as m plus 1, then I have 2m plus 2 minus 1, or 2m plus 1. So my denominator becomes 2m plus 1 factorial and x to the 2m plus 1. So now what happens with my summation, I have the m plus 2, m equals 0 up to infinity, so minus 1 to the m plus 2 over 2m plus 1 factorial x to the 2m plus 1. Well, this minus 1 to the m plus 2, I can separate that out, and I can really make this a minus 1 raised to the m power, and then a minus 1 squared. And so what happens, that minus 1 squared just becomes 1, and so I get my kind of traditional power series expansion for sine being the sum from minus 1 to infinity of minus 1 to the n, or m rather, minus 1 to the m over 2m plus 1 factorial x to the 2m plus 1. So I hope you've enjoyed this one, and now we've gotten a power series expansion from sine, for sine from our power series expansion for cosine. I will see you guys next time.